Good evening, everyone. Myself is Sharma, and I am going to take the live session for transition metal organometallic course in catalysis and biology. So this is week 2 live session where we'll be taking up mostly the assignment to solutions. But before that, I'll be discussing little about the basics that have been covered in the week 2 lectures by Professor Prasenjit Ghosh. So we will wait for 2 to 3 minutes for others to join, and then we can start with the lecture. Thank you. So now we can start the lecture. Uh, in week one, what we have seen, I'll just give a recap of it, those who have not seen or attended the lecture. So in week one, we actually mainly talked about the represynthesis. That was nothing but the kind of transformations we have seen from the acetylene molecule or the derivatives of the acetylene to different organic compounds. So mainly we have come across different basic concepts of the represynthesis, and there were certain types which we have summarized in the last lecture. One was the vinylization of acetylene molecule. So if I'll just show you the week one. So this we saw in the last lecture, where the vinylization of your acetylene molecule is one such example where you can substitute your 1H with a Cl, or say, for example, if you're treating with your acetylene molecule with HCl, so it will make a vinyl fluoride. If you are treating it with cyanide, it will make a vinyl cyanide, and so on and so forth. Similarly, the second type of the repeat reaction that we saw was hydrocarboxylation, where we could form a vinyl carboxylic acid or acrylates, where the acid would be replaced by a ester. Third type of reaction which we saw in details was ethanylation, where we could prepare vinyl pyrrolidine, which has also been asked in the assignment. And the last type of repair chemistry reaction which we saw is to how to make oligomers, or how we can have a cyclooligomerization. Say, for example, if I have 3 molecules of acetylene that could convert in presence of the catalyst, that could make a benzene molecule. That is called a conventional way of having a repair chemistry coming from your one type of acetylene. So this is the continuation in week two lectures, where we are going to talk about. First, we saw, because we ended up we ended up our last week lecture on conventional repair chemistry from acetylene, 3 molecules of acetylene giving you the benzene. How it goes, if to understand it, you have 3 acetylene. You can just see, you can mark 1, 2, 3, 4, 5, and 6. This is nothing but your CH, triple bond CH. So when we are not showing anything, that is your carbon and H bond over there. So if the bond goes and attack onto this carbon, then the charge will go onto fourth, and the charge on the fourth carbon will attack on the carbon 5, and so on and so forth. This will make a cyclic compound. So now if I'll start looking it carefully, earlier there were 3 bonds. One bond has been cleaved, one charge has been gone to carbon 3. So now there is, if there is 1, 2, 3, 4, 5, and 6. So earlier there were 3 bonds between 1 and 2. Now there would be only 2 bonds left, and a new bond would be formed between 2 and 3. So we'll make one single bond here. Similarly, between 3 and 4, there were 3 bonds. Now only 2 will be remaining. One bond, new bond would be formed between 4 and 5, and 5 and 6 would be having only 2 bonds left, and new bond would be formed in 1 and 6. So this is nothing but your benzene ring. So this is the case when we have one type of acetylene or alkyline molecule. Mainly we are talking about the synthesis of acetylene, so we are not taking any substituents. But as soon as we will increase the substituent on the acetylene molecule, say for example, you have 2 acetylenes of one type and the third acetylene is of different type. Then you can have different possibilities of products, for example, and that mainly goes through, in presence of the metal, that mainly is called as metallative repair chemistry, where if we have all the three same, then it is a conventional repair. But whenever it would be having two acetylenes or one other acetylene different, or all the three acetylenes different, then it is coming under metallative repair. So I can give you the example for this one. Say, for example, we are taking a conventional acetylene molecule. This is one molecule, this is second molecule. And a third one, which is having a substrate of X group. X can be anything. So in presence of the metal, so what will happen? Metal gets inserted between that one. So the similar way, it will get cyclized and you will ended up having a benzene ring where the metal is coordinated and X is Y. We can consider an example of palladium chloride having a benzene molecule over there. So this is one kind of, this is third kind of acetylene, which is different from the other two molecules. So this is coming under metallative repair synthesis. So as and when we increase the different types of acetylenes, the possibility of products and to come across different kind of products, the complexity increases. So if we have all the three acetylenes different with different substituents, then we might be ending up having complicated products. And this was in 1917s kind of time we are talking about. But in 2001, we came across a paper where we could see that three different kinds of acetylenes could easily give you a selective product, selectivity in the product with a proper percentage yield. So we can expect to have a good yield when we are coming. I'm talking about 2001. That was back in 1970. So here we can take the example of, if I'm having CO2 tertiary butyl, this is nothing but an ester molecule. And here it is C6H13. So we can explain this molecule as C to the bond C, and other side is having C to the bond O, and this is having tertiary butyl. And this side it is having C6H13. So the main moiety is your acetylene moiety. This is your acetylene, and that is a substrate one. This is not a normal acetylene molecule. Now, see, you can see over here. So here there is one acetylene, and the second acetylene is different from the first one. This is second acetylene, where one substrate is C6H13, both the sides, but the other way, it is having a ester group. Here it is having only a hydrogen. Now, in presence of this kind of metal-based carbene, or we can call it as a catalyst over here. So it is helping in cyclizing the whole structure. So if you'll see, earlier it was having three bonds. Now it is ending up having two bonds. So if you'll mark it over here, one, here it is two, this is three, and this is four. Now it is going like how? This is one, this is four, the bond between one and four, and this one is your two, this one is your three. So they are going in this particular fashion, and it is making a cyclic moiety involving your titanium over there. And as and when titanium goes away and you are introducing another acetylene, this is third acetylene molecule. So it will ending up having your benzene structure with different substituents. This we can explain with one more example. Say, for example, we are having these are the group, and here we are having SiMe3, SiMe3. This is one kind of acetylene. This is second kind of. Both acetylenes are a part of one molecule. And your third acetylene is different. So now you can just mark it over there to know how the bond formation would happen. The bond will be forming between these three acetylenes only. So if you mark it over here as 1, this is 2, 3, 4, 5, and 6. So these would be a substituents. So if 2 and 3 makes one bond, the charge will go onto the 4th, and 4 will go and make a bond with 5, and then charge will come on 6, which will go and make a bond on 1. So this is the basic mechanism to understand the bond formation over here. So what we can expect now, these substituents will be like that only, the way they were before. Now if you'll see, the carbon 1 and 6, they were having no bond earlier, but now when they will be, now when they will be making a bond, it would be making a 5-membered ring, 1, 2, 3, 4, and 5. So we can close this ring now, making the numbers properly, 1 and 6. Now you can see 1 and 2 were having 3 bonds earlier. It would be having only 2 bonds left. We'll make 2 bonds, marking it as 2. Now carbon 2 was having a substrate of SiMe3. We will form SiMe3 over here. Now 2 and 3 is having 1 bond. We will form 3 here. 3 and 4 would be having 2 bonds left. So I'm marking it as 4. 4 and 5, again, they are having 1 bond newly formed, and 5 is having a substituent of SiMe3, and 5 and 6 are being left with 2 bonds again. If you will rearrange it, because this is a benzene ring, so it will take up the most stable form, where we can just formulate it as SiMe3, SiMe3. Here it formed a 5-membered ring with substituents of O-xyl, so on. So this is your product. I hope you understood. Is there any question? You can drop a message in the chat box, or you can unmute yourself so that we can move further. So we have not started actually the week 2 thing, because it is based on metathesis that we are going to take up today. But this was a part which has not been described in the last lectures. So this kind of question has appeared in the assignment. So the explanation of that kind of product, how we can come up with the 3 different acetylenes or 2 different acetylenes and coming up with this particular product, how the mechanism works. So this is the explanation. This is directly the first question of your assignment for week 2. So if there is no further doubt, so we can take up the main topic of our this live session. So this is another example where, okay, this is a continuation of your metallative repe synthesis, when we are having different types of acetylene. So this kind of formation you already saw here. I just explained. So this kind of formation, how we started with one acetylene is this one, second is this one, third we were having at this particular stage, and we were having TiX3 over here. Now this TiX3 can be easily replaced by any proton source or I positive source. So when you are having H positive or a deuterium positive, so this TiX3 can leave easily and it could have your H over there. Similarly, when you are treating this molecule which has come from acetylene only. So don't forget that is a repe chemistry. So its origin sometimes in the question that will start with, that will give you a product over here, and they can ask for the origin of this kind of product. So don't forget that the origin has been always the acetylene, and that comes under repe chemistry. That too, a further distinction of it, methylative repe, where it is involving 3 different types of acetylenes. When you are treating it with the I2, then it will form an iodide version of here. And when you are treating it with the benzaldehyde, it would cyclize the product, because there is, you are having C double bond O thing, and here you are having C double bond H and PH. So it can cyclize and can release a product, and then you can have this kind of product with 49% yield, which was not possible in early stages, but in 2001 it could easily be devised, like how we can have different kind of products with good yield, good selectivity, with the acetylene in reprochemistry. So now the topic of our week 2 session is metathesis reaction. So here in the week 2 lectures, what has been taught, they have mainly professor has talked about the introduction or the history beyond your metathesis, which is very, very important because there are many scientists who have postulated many mechanisms, different mechanisms that we will take up today into consideration. And what is the final mechanism that has been followed till date? So as you know that metathesis reactions, they are very important in polymer chemistry. In 2005, Nobel Prize has been given. These are the name of the person, and to draw your attention, he is the person who has actually given the right mechanism for the metathesis, which has been seen in the reactions of the grub and shock. So those people have given the evidence for the right mechanism for proving the mechanism which has been postulated by Chopin. So mainly when we have a alkene metathesis, so which has been given by Caldron, which is a cyclobutane. So remember that whatever the names that we are going to talk about, the scientist names that we are going to talk about and their postulated mechanisms, the questions could be directly coming in the paper that who has given what mechanism. So this is also very important. So if we talk about firstly the metathesis reaction, metathesis, what is metathesis reaction? So before going and explaining this in details, we would just take up for little introduction of it. So what has been seen that if I am giving you, so if I am having this kind of molecule CH3, CH, double bond CH, and CH3. So this is nothing but your 2-butene. How? 1, 2, 3, and 4. So this is just basic nomenclature. The double bond is starting from the 2, so it is 2-butene. And when I'm treating it with its deuterated version, which is CD3, CD, double bond CD, and CD3. Instead of the hydrogen, now instead of the proton, we have a deuterium. So this is your deuterated deuterium. So when the catalysis will happen and we could identify the products, what kind of products we could get over here. So what really happened? So just simple mechanism. If I'll make it even more better way. Okay. So if I'll just take this particular thing and we just have to cut and stitch whatever we are having onto the other parts. That is called your pair-wise mechanism. That means if A double bond B and C double bond D is here, then A and C would make a pair and B and D would make a pair. So this is called cutting and stitching mechanism. This is for the layman language, like anybody can understand it very properly, but how it happens, we will take it in further details. So we cut it from this part and we stitch these two parts, similarly happening over here. So we will be ended up having CH3CH double bond, and the other part I could take from CD3. So this would form as 2 times. So that would come as your major product. So how do you explain these kind of examples or mechanisms? So these kind of reactions comes under metathesis reactions. where the different moieties are on your alkene bond, they could cut and to stitch to some other alkene over there. Similarly, so keeping that in mind, if we will take up another example, like if I'm having a C14 labeled propylene, that means if I'm having C propylene means three carbons, CH2 double bond. Since it has not been mentioned where the double bond is, so it can only be having the double bond at first position. So if we are labeling the carbon, second carbon and CH3. So label means normally isotope that we have is carbon 12. Carbon 13 is even more less percentage, and we are labeling it with carbon 14, which is having even more less percentage. So we have labeled it with 14 carbon C to identify, because if we have labeled something and if we are getting a product just by the mass spectroscopy or by the IR spectroscopy, we could easily see the shift in the wave numbers and the mass value. Say, for example, if your mass value is X for CH2 double bond CH and CH3, where your carbon is 12 and your product is having M plus 2. That means the labeled carbon has been put into your product. That's why the mass has been increased by 2 units. Similarly, if we are having IR, we are recording the IR for this one. So there would be C double bond C stretch, C single bond C stretch. So carbon 12 and carbon 12 and combination of 12 and 14, that would make a lot of difference. The shift in wave numbers we can easily see, and that would make a lot of difference to identify the product. So when we have, that's why the labeling studies make a lot of difference. So when we have CH2 double bond C star H CH3, that is labeled propylene, C14 propylene, and another molecule of CH2 double bond C star H CH3. Now, as I said, if we go by the pair mechanism, so it would form this cut and stitch over here, these two parts cut and stitch over here. That would be CH2 ethylene molecule and C star H double bond C star H having CH3 and CH3. Right? So this is one possibility. So this is only possible when we are talking about a pairwise mechanism. That means whichever is in what direction. If A and B are here, then they both will combine together to give you one product. If C and D are here, they both will pair up and give you. Then there is no cross coupling. There is no cross bonding over there, which does not come under pairwise. But if we talk about non-pairwise, then it could ended up having different products. So CH2 double bond C star H CH3, CH2 double bond C star H CH3. Now, if I talk about non-pairwise mechanism, where it would again cut and stitch your alkene moieties, but it would go in a non-pairwise. So this will go and combine with this one, and this will go and combine with this one. Ultimately, they both have same product. So the major product could come as CH2 double bond C star H CH3. So again, this could also be formed, but that would only be your starting material. So what kind of products that you are getting by labeling studies, if you saw in mass difference, if you saw the difference in your IR, you can identify the different possible products over there. So the main question arises here, like how the metathesis reaction is proceeding, how it is actually proceeding. Now, in this particular statement, we have different kinds of mechanism given by different people. Say, for example, as I said about the Calderon, who gave the mechanism involving cyclobutane as an intermediate. So, just an attention over here. this meeting would be finishing up in next 10 minutes. So I would request you all to join again on the same link, as the Zoom meeting is having a limitation of 40 to 50 minutes. So sorry for the inconvenience, but do join the same link if you're in the meeting. Thank you. Okay, so as we were talking about, now we understood the concept of having different alkenes and how the product would come into picture. But there are different hypotheses of their mechanism. So we'll take up one by one in details. So in Calderon, this is the reference for the paper. You can go back and check it also. So different experiments have been performed to prove their hypothesis. So Calderon has stated that if we have A and B, this is your one alkene, or you can call it as an olefin. And this is your second olefin, where your A, B, C, D, anything, these could be any substituents. So in presence of the metal, what will happen? So when we are having these bonds, the double bond will start cleaving up and the new bond will start making up between B and D. Similarly, the double bond between C and D would start cleaving up and the new bond will start making up in A and C, which will tend to happen this kind of cyclobutane intermediate. And as and when the metal goes out, it would pair in this particular fashion. As I said, the pairwise mechanism, A and C having this particular bond, rearrange after rearrangement, and B and D would form another intermediate. So in our, so first thing is from the Caltron, where we could say that he has talked about cyclobutane intermediate as a possible mechanism, or the possible intermediate which is involved in carrying out the metathesis reaction. So this is one such reaction where we saw if we have A and B, and if we have C and D, so what will happen? I would just make over here. So this would be breaking, this new bond would be making C and D, A and B. Now this, again, this double bond was broken and the new bond between A and C has been made. And once it is rearranging, all the bonds would be rearranging. Similarly, the single bond could also be broken between these two. And therefore, we will be ending up having this kind of cyclobutane intermediate, which is having a metal, because the electrons are there, so it would bound with your metal as a coordination chemistry, coordination complex. And once this loses the metal, it would now have this kind of pair. A and C would make a double bond, and B and D would make a double bond. So what we started with, what we are ending up with, that is called as metathesis reaction. There could be other combinations also, but in pairwise mechanism, there is no further product could be possible, but only these two. So is there any question till now, or we can move ahead? You can even put your questions or any query in the chat box also if you don't want to unmute yourself. Or it would be better if I can hear your question properly. Okay, so if there is no further question, we will take up the next thing. So, okay, the meeting is going to finish in 5 minutes. So I am ending up this meeting over here. I would request you all to rejoin the same link. I'll start the meeting in that one. Please rejoin it. Thank you.